To Team 29's Project 2 presentation, Modeling Energy Storage Systems. Throughout this project, we will be solving the grand challenge of making solar energy economical. Our problem is that solar power is a common energy source, yet it's sometimes unavailable. For instance, no energy can be captured during nighttime, and about 10 to 25% of normal power output is captured on cloudy days through solar panels. Hydroelectric power can be combined with solar panels to satisfy energy needs. However, the total cost and efficiency of the hydroelectric dam that is designed must be reasonable. Some of our team's objectives included having an efficiency of 80% plus or minus 5%. Typically, the efficiencies of hydroelectric dams are around 90%, so our efficiency seemed pretty reasonable. And we also wanted to keep our cost under $1 million. Above all, as well, we wanted to make ethical and environmentally conscious decisions throughout our planning process. In order to successfully execute this project, we started out by weighing the pros and cons of each site that we were given to build our dam on. We also created code to evaluate these specific decisions and made decisions weighing the quality versus cost of materials for our efficiency. Finally, we accounted for an extra problem that may arise with the use of a hydroelectric dam, which Dan will talk about in a minute. And we also evaluated these decisions at the end to determine if the best choice was made.
The theory behind our work. The code was programmed to calculate the area of the reservoir, energy input required to output 120 megawatts, our overall efficiency, and as well as the fill and empty time of the reservoir. Our energy was removed throughout the system based on pipe friction and turbulence during the pipe bends, as well as pipe clogging, which we factored in as 10% of the pipe. We thought this might occur as possible debris and leaves and mud builds up in the pipe throughout time. We also factored in turbine and pump efficiencies into our energy equation, and all of this ended up being placed in a universal accounting equation to calculate what energy would be required as our input in order to get our 120 megawatt output. You can see these equations as well on the right of the theory behind the work section. The pump loss function is based on the pump efficiency as well as the energy input. The turbine loss equation is based on our output energy as well as the turbine efficiency. Our pipe friction equation was based on the mass of our water as well as the lengths and diameters of our pipes and the friction coefficient for the pipe. And that was the same for the friction on the way up as well as on the way down, although the velocities did change from up to down. Lastly, we had to factor in turbulence that were created by the bends, and we did this using the pipe bend coefficients as well as the mass of water and the velocity of that water. Here we can see the actual code. We start off with importing math. We then define several functions, such as functions for pipe, friction and bend friction and turbulence, as well as turbine and pump efficiencies. We then go down and we start declaring variables for pump efficiencies and pipe diameters and lengths, and then we begin to calculate things like elevation, velocities of the water. We then go into the energy calculations, and down here is where we use our universal accounting equation in order to calculate the energy input required to get our 120 megawatt output. We then calculate the efficiency, and here we output all of our calculations, which then, as we can see on the right hand side of the screen, come out with an efficiency of 83%.
When our team was considering which site was optimal for our dam, our main two concerns were cost and efficiency. To compare these sites, we compiled all the information listed below into a chart to qualitatively compare the site options, and then went on to calculate actual efficiency and cost in order to quantitatively support our choice. So the Site 1 costs, besides the equipment used, included access to the road, which would be $40,000, site preparation at $18,000, and then the extra costs for Site 1 included those for chemical testing. According to the site description, due to prior agricultural use, there was the possibility of herbicides or other chemical agents in the soil, which could cause difficulties when building our dam. So we would initially need to test for these chemicals, which would cost us $10,000. But then, depending on what we found, extra costs could be added depending on what types of chemicals were in the soil, and this could cost us up to $300 to $510 per metric ton of soil being removed to build the dam. So that is a very large unknown in our cost calculation, but without including that, the cost for Site 1 would be about $391,017. When considering the efficiency for Site 1, we looked at the fact that it was a smaller distance from the river, so we would need to use less pipe, as well as the fact that there were only 2 bends in the pipe, which would reduce pipe friction. And there was also a smaller incline, which would be better for the pipe bends as well. When calculating this efficiency for Site 1 using our code, we found that it would be about 83% efficient. Going on to Site 2, some of the additional costs were an access road as well. This access road would be quite a bit more expensive than the access road for Site 1 because the river is further away from the road, so it would be about $100,000. Site preparation would be a bit more expensive than Site 1 at $36,000, and then this site also came along with the fact that local indigenous people expressed concerns that the land may have been used as an ancestral burial site. So costs would include investigating this burial site, which would cost about $8,000, and depending on our findings, we would have to determine what to do with the burial site. We could consider moving the graves, and with some research, we found that that would cost about $2,000 to $7,000 per grave, and we are still unsure if we would even be able to make an agreement with the indigenous people to move these graves, so that comes along with a lot of unknown costs as well. When estimating the cost, not even including the possible burial site removal, the cost was about $696,200, and the efficiency considerations included things like a steeper slope, as well as the 2 bends in the pipe and a longer distance from the river. When we actually calculated this efficiency using our code, it was around 80%. For Site 3, some of the additional costs included again the access road, which was even more expensive as this was the furthest from the road, and then site preparation, which was in between Site 1 and 2 at around $21,000. This site came along with the fact that there was quite a bit of soil erosion, and this is what's mainly responsible for the change in slope that would be causing 3 bends in the pipe instead of 1. We would need to do some research on this soil erosion and institute a mitigation strategy, which would be $1.60 per square meter of our dam. And based on the effectiveness of that mitigation strategy, it might also be necessary to include some possible erosion monitoring in the long term to make sure our dam would still be stable even with possible erosion, which obviously has a lot of unknowns for our design, as well as the cost of this erosion monitoring. Because of this, we didn't even go on to calculate the efficiency of Site 3 with our code, but we did look at the fact that the pipe would have to have at least 3 bends and the distance was very far from the river, so we determined that the efficiency would be much lower regardless of testing it with our code. Because of all the things discussed, our final decision did end up being Site 1. Not only did it have the highest efficiency when tested and the lowest cost, but also there were less unknowns. With Site 2, we weren't really sure how to deal with the burial site, and the costs for that could be very expensive. And with Site 3, the possible erosion could be very detrimental to the design of our dam and also very expensive.
To decide on parts for our design, we created decision matrices that emphasized efficiency. Then we would run the combination through our code, and if the price was unreasonable, we adjusted the part until we achieved a happy balance between price and efficiency. Overall, in our final design, we used a premium pump with an effective performance rating of 40, which cost $20,080. For pipes, we used Glorious pipes with an internal diameter of 2.5 meters, which cost $39,310.08. The pipes had 2 bends total, each 30 degrees, which cost $1,032. For turbines, we used a Mondo turbine with an effective performance down of 40, which cost $27,090. Other costs we had to account for were the installation and construction costs. The on-ground pipe installation cost $33,541.02 for the 67.1 meters of piping. Additionally, because the length and width of the reservoir is 268.3 meters with a depth of 10 meters, the reservoir wall construction cost $101,964.70. The reservoir would take 5 hours to fill and 6.67 hours to empty. In conclusion, our target efficiency was 80%, and we met our expectation with an actual efficiency of 83%. Moreover, our price cap was set at $1 million, which was much higher than our actual price of $391,017.80. However, this price could change if significant chemical damage is found from herbicides. Finally, our design would need an energy input of 144.01 megawatt hours to operate. Thank you.